Hi, everybody. Welcome back. So I'm Gautam. I'm the study lead from JPL. And so it turns out that after you've built your complicated instruments and you start to take images, you still have to find the planet inside your image, where every point of scattered starlight actually mimics a planet. Okay, and there can be thousands of these in your images, and so you really have to find the right object. So to give a talk on this issue, we decided that for this workshop we'd have an outsider's perspective. So I met today's speaker a few years ago at Palomar Observatory when he was a hired gun working on how to extract planet images from integral field spectrograph data. And since then, he sort of disappeared, but is now thinking about coming back into the field again. And so it is my distinct pleasure to welcome Rob Fergus as today's speaker. Rob is an associate professor of computer science at the Keck Institute of Mathematical Sciences at NYU. So this is an institute that does applied mathematics and computer science. He is also a research scientist at Facebook, working on artificial intelligence problems. His research basically focuses on computer vision, machine learning, and artificial intelligence. And I think he's especially interested in deep learning problems for object recognition. He received a master's degree in electrical engineering here at Caltech, working with Pietro Parona. And then he moved on to finish a PhD with Professor Andrew Zisserman at Oxford in 2005. Before coming to NYU, he spent 2 years as a postdoc at CSAIL at MIT, working with William Freeman. Rob has received several awards, including the CVPR Best Paper Prize, a Sloan Fellowship, an NSF Career Award, and the IEEE Longuet-Higgins Prize. So without much further ado, we have Rob Fergus on machine learning for astronomy.
Thank you, Gautam, for that great introduction. Okay, so I'm very much the outsider here, so I've tried to put together a bit of a talk which gives a sort of high-level view of machine learning. Obviously, I can't really hope to try and summarize the entire field in just 45 minutes, but I'm going to try and focus on a sort of, I think, a fundamental philosophical difference between different families of machine learning approach. And one approach is going to be called generative modeling, the other discriminative modeling. And I'll try and highlight some basic techniques you might be familiar with, and just explain how they fit into these two different philosophies. And then I'll essentially try and look at how you can apply them to some of the problems that are relevant to this workshop, and in particular exoplanet detection. So just to get going, we're going to start off by thinking about a very, very simple toy data set. Okay? This is just a 2D set collection of data. You can see on the plane as follows. We're going to assume each data point has been given a label, and that's being shown by the color you see. And our objective here is to somehow take this data, we want to fit a model to it that will enable us to predict the label of a new data point that we're going to be given. All right? And there are basically two sort of philosophical approaches to how you might go about this process. And what I'm going to do is just look at the math to start with, and then I'll come back and show you the sort of visual analogy. Now, so essentially, you're going to be given this new point x, and what you're trying to compute is some sort of probability, the probability of the class being red given that new data point. And that's something called the posterior probability. And then if you use Bayes' rule, you can flip this around to compute something called the likelihood, which is, if I know I'm looking at class 1, what would be my probability density over the inputs over the space? And then if I stick my new data point in there, what would its probability be? And then you also have a prior, which essentially tells you the prior probability of the different frequencies of the two classes. And it's a proportionality here because there's a denominator term, which typically we don't worry about too much. And the reason is that if all you're interested in is trying to do a classification, we'll talk about other problems beyond classification in just a moment. But just for classification, you can get away with computing essentially a ratio here between these two probabilities. So the probability of class 1 given the new data point divided by class 2. And so that denominator term cancels out. And then you're just left with another ratio here of now likelihoods and this prior ratio as follows. Now, in discriminative modeling, what you're going to be doing is you're going to be fitting a function directly to this quantity here. Okay? And in generative modeling, you're going to be fitting this one. And this seems like a sort of, well, isn't this just sort of a pedantic difference? But the answer is not quite. And it does actually have, I think, an important, certainly when you think about how you might apply machine learning to astronomy, these two different schools of thought do actually end up producing quite different approaches. So let's just look at the generative one for a moment. So what this is really saying is you have to build now, in the generative model, what you're building up is basically a little you're building a model of the data density. Okay, so that each one of these, now if you have labels, we can afford to build a different density model for each cluster in turn. So the idea is you're going to your model will have some parameters theta. So theta1 will be the parameters for the first class, so this one, the red one. And you're going to be, what you would do in the training phase would be to estimate the parameters, in this case, the mean and covariance matrix of your Gaussian, to just optimize, to maximize the likelihood of the data. So you're going to sort of twiddle the theta so that the data points that you have in your training set, you maximize their probability. And then similarly, you would do the same thing for the other class. Now, the key point is, sort of from a sort of high-level point of view, what you're trying to do is it's a sort of top-down explanation of the data. You're adjusting those model parameters so that you can best explain the data that you see. Now, what we will then do, so that's the sort of training phase of the whole setup. What you then do is at test time, you'll be given a new data point, and then you can stick that new data point in and compute its probability under the two density models, okay, under the red density and the blue density. And then that gives you this likelihood ratio, and then you can combine it with your priors to give some the posterior ratio between the two things. So implicitly, there is actually a decision surface between these two, between the two classes, the dashed line that I'm showing, but you're not modeling that directly. Instead, what you're actually modeling is the actual distribution of the points. In other words, when you fit this model, you're caring about this guy over here, which is really a very long way from the decision surface. Okay, so if you have a finite amount of modeling capacity, your model will be spending a lot of time fiddling around trying to fit stuff over here and over there, and not that much. It's not really directly concerning itself with trying to get this decision surface correct between the two. Now, in discriminative modeling, you don't bother creating a density model at all. All you're going to do is actually just fit directly some function that will is effectively going to be this posterior ratio, the quantity. That was the left-hand side of that Bayes rule thing I showed earlier. And in this case, your decisions, you can choose it's your choice what that decision surface should be. So in this case here, it's just a line, so that we would simply be adjusting the y-intercept and the gradient of that line such that we don't misclassify any of these points on our training set. Okay? And then, given the new point, we would be able to stick it in and then evaluate it under this function, and that would tell us which side of the decision surface we're on. So philosophically, what you've done is you haven't bothered to create any, you have no idea what's going on over here in these parts of the input space. All you're focusing on is exactly just, is this part here, where the sort of the borderline points, as it were, they're going to influence the choice of the parameters of your line fit. Okay, now, so just to, what I'm going to try to do with the rest of the talk is to try and show you different methods that fit into either this generative or discriminative approach, and try and sort of contrast and compare them. Okay, so one simple one that is a nice generative model, although it's strictly speaking not a true generative model, but we'll come to that in just a second, is PCA. So hopefully most people have at least seen this in some form. The idea is you're given some data points in some high-dimensional space D. You're trying to find a sort of low-dimensional version of them, Z, and so they'll be sitting in some low-dimensional space M. So M is going to be a lot less than big D. And so you can think about this, the objective now is no longer classification. You can think about this as a kind of compression objective. And what you're trying to do is to sort of reconstruct some approximate version x tilde of the original data point given your the coordinate in your low-dimensional space. And you're going to do that using a linear basis W plus some sort of mean offset B. Okay? And then your objective function is going to be to minimize the Euclidean distance between your sort of reconstructed version of the point and the original. And just the math's a bit daunting, so let's just look at the picture. This is really what's going on. So here we have some two-dimensional data. We're trying to project it down to a one-dimensional space, the purple line. The little reconstructed versions of the points are shown in green. So we want the distance between the green point and the red point to be as small as possible. And our objective function down here, I'm sorry, it's a little bit clipped off. You can think of this as an L2 term. This is like a spring. You're trying to minimize the spring energy by wiggling this purple line around simultaneously with sliding the little green points along the line. That's the rough idea of what you're doing when you do PCA. So of course, this is just a sort of two-dimensional to one-dimensional projection. In practice, of course, you can choose an arbitrary number of dimensions as your input space, an arbitrary number of dimensions, although it must be smaller for your embedded space. Now, and it turns out for this type of model, you have a nice closed-form solution for figuring out this linear basis. You can do an eigendecomposition of the covariance matrix. There are actually other ways of doing it, using sort of iterative algorithms that have benefits if you have lots of data. And you can think of this really as a generative model. So just to make that a little bit clearer, there is actually sort of a probabilistic interpretation of this whole thing, where you would have some now prior distribution over your variables in your latent space, that is the sort of low-dimensional coordinates. You assume it comes from some zero-mean Gaussian that's isotropic. That would give you some offset from some mean location that gives you this point here. And then you would add isotropic noise that goes out away from the manifold into the high-dimensional space. And you end up with a full sort of density model of your data. And that's effectively what you're fitting when you fit PCA. You're fitting a little density model. Now, normally you don't worry about this sort of probabilistic sort of, topping on the cake, as it were. You just worry about just getting the linear basis and the mean offset and things like that. But the point is that in this thing is you can think about you're sort of effectively generating your data points from your underlying model. That is, you have some process by which you can take a random variable in and sample through the model to end up with a data point that will sort of basically be similar, have the same distribution, hopefully, as your original the original data that you're given. Okay, so that's a sort of, so PCA is one example of a generative model. A classic discriminative method would be something called a support vector machine. So in this case, this is something where they have a formal notion of, so in this little toy example I was showing previously, I was using a line to separate these two distributions in a classification problem. And the SVMs give you some formal notion of how to pick that line, so-called to optimize this thing called the margin, which is this kind of gap between the two. This gives you guarantees about generalization. So generalization is the ability to sort of, the prediction you make when you train on the model on a training set. You want the predictions you make to sort of hold to some held out set of data. And if you're not careful, if you pick the decision surface to be some sort of, diagonal that grazed one of these other points, you can see that you'd be very sensitive to kind of noise and where the points were, and therefore you might make mistakes when you came to some held out point at test time. Now, in this case here, of course, again, the decision surface is linear. You can there's ways to sort of do something called the kernel trick, which can give you nonlinear decision surfaces, polynomial or much more complicated ones, and that involves some sort of projection of the data to a high-dimensional space and doing a linear decision surface in that high-dimensional space. The other thing to say, of course, is in this case the data is separable. The two classes are perfectly separated. In practice, you can introduce slack variables to handle the case where you have non-separable data. So SVMs are a very powerful, widely used piece of machinery. Now, one thing to say about these discriminative models is that they are very, it's in some sense quite simple machinery, right? You're just putting in the way these things work is you put in a data point and you get out some prediction. In the generative model, there's always a business of sort of, figuring out the sort of latent variable. If we go back to this thing, for example, if you're given a new data point, you have to figure out essentially the latent variables in your model for that particular new data point you're given. In PCA, it's straightforward. In many other more complicated generative models, it's not so easy. Now, one thing I'm going to now talk about is a bit of a detour. So these discriminative approaches, for a long time in sort of when people in fields like computer vision, which is my home field, there were a whole bunch of approaches that were either discriminative or generative, and neither of them work very well. And I guess, I feel I have to tell you about a very big breakthrough that's happened in machine learning in the last couple of years, which is essentially basically big neural nets being applied to these types of, they're a form of discriminative model, and they've been proven to be very, very effective at a range of tasks with natural signals. By natural image, I mean the type of image you might take with your camera. Okay, so this is a photograph of the natural world. And so the types of, we've seen huge gains in performance in computer vision, also for speech understanding, and these algorithms are now running in your smartphones and things like that, and also indeed for things like natural language processing too. And so this represents a bit of a detour. So this is just we'll come back to the astronomy part in just a few minutes, but you'll see that they can be very powerful models indeed, and indeed very useful for astronomy problems too. So the three ingredients really are that there's this very big neural network model, which is going to essentially take in an image as an input and spit out some sort of label, which we'll see in a moment. And it's discriminative by the meaning is we don't model the distribution of natural images in any way. There's no data density model of what it means to take a picture in the world. So we have a big model. It's going to be trained supervised. That is, for each image that we are given in our training set, we know what the label is. Okay? So unsupervised means you're just given the image. If you give them the label as well, then you can do supervised training. And in fact, discriminative approaches, as I'll discuss at the end, can only be trained with labels. And we'll see how that you have to sort of contrive labels if you don't have them, if you want to apply these types of model. The second ingredient is huge labeled data sets. So if you want to make these models big to be sorry, let me back up. One attractive feature of discriminative modeling is you can build very, very large models easily. And that means you can create incredibly complicated decision surfaces. Instead of this straight line here, imagine these points were now photographs of different types of animal, and you want to separate them. You would need an incredibly complicated decision surface to do it in the original pixel space. But these big deep networks do exactly that. They can create, as we'll see, sort of exponentially complicated decision surfaces. And so you need lots of data to train those very complicated models, right? And the third ingredient, of course, is lots of computation to crank this big model over lots of data. So just to show one particular task where they've demonstrated amazing gains, was image classification. So you're given a bunch of images like this. There's a ground truth label that's come from, they were gathered from the internet, so we know what the ground truth is. And the machine is going to make a prediction. This is showing the top 5 predictions along with some confidence. And we're going to score them correct if the correct answer is in the top 5. So that's the particular problem I'm going to talk about. There's a particular variant of these neural network models, something called a convolutional neural net. It was actually a very old model invented by my colleague Jan LeCun. He's now a colleague of mine at NYU and Facebook, but he used to be at Bell Labs when he came up with this. And it's essentially a convolutional network where the topology of the network has been sort of adapted to data that lies on a 2D grid, like an image. And there was a sort of breakthrough paper a few years ago from Jeff Hinton's group at Toronto, where they basically took that model of Jan's, just scaled the whole thing up. So instead of being a few layers, it has 8 different layers of representation. So the classifier part is really at the top here, where you're trying to classify one of 1,000 different classes. And these layers are going from the pixels, extracting successively more complicated feature abstractions of the input all the way up so that they can then make a prediction as to whether it's a cat or a dog or a goldfish or whatnot. Okay? And that the parameters in these layers have parameters in that will be attuned to minimize some sort of classification error at the top. Okay? And that the whole algorithm is trained by backpropagation. That's effectively the chain rule by taking an error signal and backpropagating it through the network. And there's really quite enormous models, right? So they have 60 million parameters in. The thing's trained for 2 weeks on GPUs. And so to train, to have that many parameters and not overfit your training data, you need really a lot of it. And so in the last few years, basically, the training data set sizes have got big enough. There's been huge efforts with Amazon Mechanical Turk to label them. And then that's enabled these big models to be trained effectively. And the other thing to say, of course, is the GPUs, right? So now the most powerful GPUs are incredibly powerful. So one card is as fast as the world's fastest computer around 2000. So what happened was, before these combinets came along, this was the best performance in this. This was a sort of computer vision benchmark competition that was run by Stanford. This is error, so you want to be low on this axis. For the last few years, the errors had sort of plateaued fairly. There wasn't really significant gains. And then in 2012, that big paper from Jeff Hinton's group came along, and there was an immediate dramatic decrease in error rate. And the even more remarkable thing is, in subsequent years, what's happened is that the error rates have gone even further and further down. So the point now, they're actually better than humans on this data set. Now, of course, the data set is somewhat constrained. Just to give you a feel, so I took some photos on holiday, so this couldn't possibly be in the training set, just to give you a feel of how well they work. So these are just top tags attached to this image. So you can see it's getting a lot of the sort of, the feel of the image pretty nicely. This is one just showing, it seems to, for some reason, thinks it's in Helsinki. It's actually in the Mediterranean. And I did give it a very hard one. So this is actually an underground cave. And I think it's getting confused with the Sagrada Familia in Barcelona. So while these numbers on these benchmarks do look very impressive, they're still not yet at human performance, but I should say that the performance jump is enormous, and it's gone from being on a technology that was sort of just in academic research to now being used in industry. So I've been on leave at Facebook for 2 years, and this is my sort of day job, is helping them get these models up and running. And so Facebook gets 1 billion images a day uploaded to it, and 2 of these models look at every image now. One does fit the face recognition, and the other one recognizes things like offensive content, and also telling whether you've got a dog in your photo and stuff like that. And one of the beauty about these models are they're very, very fast at test time. They're a pain to train. They take weeks to train, but you can train. But really, a single GPU can run hundreds of images a second, if not more now, on them. So they've really had a huge impact in practice. And what people are finding now is that they actually work incredibly well for other types of imaging data. So medical imaging, like 3D scans, 2D scans, stuff like that. They work great. You can even represent speech as a 2D image, like a speech spectrogram, and the latest speech recognition technologies use ConvNets, very similar to the ones used for image recognition. And I was also talking to some particle physicists a few weeks ago. They're using them to classify different types of subatomic particle automatically. And if you do have data with other types of dependencies, like some sort of temporal dependency, then there are other types of network, like a recurrent net, that are appropriate. Now, the one caveat is that all these models, they're incredibly powerful, but you need tons and tons of labeled data, right? So for each one of those training images of a dog, some human had to say, that's a dog, okay? And so, it is a big constraint. Right? So, for example, in a lot of the astronomy applications, you may only have 5 exposures of a given exoplanet or something like that. And so it's like, how would you ever use these models? Okay, so I'll talk a little bit about this coming up. Okay, now, one direct application of this type of ConvNet was this is coming back to astronomy now, was to do, for example, galaxy morphology classification. So the folks at Galaxy Zoo had this quite complicated taxonomy of classifying different galaxy shapes. They got humans to do this through Amazon Mechanical Turk and some sort of competition. And so they were able to get a very, very large data set here of human-labeled galaxies according to this taxonomy. And there was a nice, they actually then had a Kaggle competition where they tried to see whether they could get machine learning algorithms to do the same task. And they could use those labels from the Galaxy Zoo effort as training data. So what they did was to take the picture of the little galaxy and throw it into one of these ConvNets. So this is actually the same sort of architecture that I was just referring to. They did have some slight twist here to exploit the rotational invariance of the image. And what you can find is actually that the ConvNets will do about as well as they were actually trained to sort of match human prediction. And you can see that actually you can do that very closely. So this, I think the blue is the algorithm and the red is the human. Okay, so they can work basically at sort of human performance for this kind of task. So this, now if you have new large surveys, you could run these kinds of algorithms to automatically classify your different galaxy types. Okay, so now I wanted to just talk a little bit about the exoplanet detection. So I did, a few years ago, I was working with Gautam and Rebecca Oppenheimer and others at MNH, and I helped them a little bit with some of the speckle processing. So this is an algorithm that I and my collaborators at the time came up with. This is data that, we applied it to data from the P1640 instrument. So this is essentially integrated spectrograph. We're looking at different images here at different wavelengths. So it's near infrared, and these are the blobs you see are the speckle artifacts that we've been hearing about in previous talks. They are, because they're diffraction-based, they evolve radially with wavelength, but the planet is stationary. So there's a planet signal. This is, I think, HR8799, so there's some planets buried under all this. And hopefully, the question is, can we sort of remove the speckles and find the planets? Now, one thing I just wanted to say is that I'm not trying to sell this algorithm. I'm going to use it as an example to illustrate the differences between generative and discriminative modeling. Okay, so now to do that, to make the differences between the algorithms as apparent as possible, we're going to use a common representation for the different versions of them. Okay, so the idea is that what we're going to look at is we're going to take a little annulus of that cube we saw in the previous slide. So instead of working in Cartesian reference frame, we're going to roll things out into sort of a little polar annulus. So there's the radius here across the annulus. Here is the angle. And what we're going to do is to take little slices at given angles. And so the slices going sort of into the wavelength direction. So what we now see is we have a sort of little data patches, if you like, are going to be radius on this axis and wavelength. So those speckles that we saw moving radially outward now become diagonal structures in this. Now the planet, though, which doesn't move as a function of wavelength, will be a vertical structure, like here. So obviously it's not that bright normally. I'm just showing you an example where it's clear to see. And the question is, can we sort of design something that will kind of separate out, will tell that this is a planet and then this one didn't contain a planet. Okay, so I'm going to go through 3 different types of algorithm. So one was something called DS4 Detect. So this is going to be a generative model based on PCA. And then there's some colleagues of mine. So Bernhard Schorkopf's a very famous machine learning researcher in Germany. He's a Max Planck director, and he's very interested in astronomy. And so he worked with Ricky Nielsen, who's maybe in the audience. This is one of his machine learning students. And they came up with a discriminative version of this algorithm. So you'll be able to directly sort of contrast and compare how you would apply generative modeling and discriminative modeling to the same data. And then the third thing I'll talk about is an algorithm that once you've detected the planet, doing a slightly more sophisticated model that tries to estimate the spectra of the planet signal. And the key point is they're all using the same input representation, the same data. All that's changing is the machine learning approach. And as I say, there's a whole bunch of other speckle suppression algorithms that are actually quite related to these things. But I'm not sort of going to compare to them here. I just want to sort of compare the machine learning differences rather than the overall algorithms. OK, so for the detection task, the basic idea is we're going to be taking these annuli from the cubes. So this is the annulus here. One important thing you need to do is you need to make sure that we sort of hold out the region we're going to probe from our training set. So we're going to fit the generative or discriminative model. What we're going to do is to sort of leave out from the training data the region we're interested in sort of detecting. And so what we're going to do is for each potential position in the input cube, we will take, so this will correspond, this point here will correspond to this little purple region. And we're going to fit the model on the green stuff and then evaluate it in the region in purple. And this is actually very important because you don't want the model to sort of overfit to the planet itself. And so you want to see whether it can generalize to this new region. So as a result, what's going to happen actually is that you have to iteratively not only iterate over wavelength, but you'll have to build a new model for every single radius and wavelength offset from the center. Okay, so it's somewhat painful to do, but you can, if you have powerful computers, you can afford to do it. Okay, so let's look at the DS4 Detect algorithm. So in this one, what we're going to do is basically use a very simple PCA-based model. So we're going to take those little patches, we're going to build a PCA representation of them. So this is a low-dimensional projection onto, say, 20 different principal components. And this is just showing you the spectrum. This is the eigenspectrum of the covariance matrix. So you can see that with 20 principal components, we've got most of the energy in the signal. So even though the speckles are very complicated, they're intrinsically somewhat low-dimensional. And the idea in this algorithm is supremely dumb, but the sort of quickest thing and easiest thing to do to start with, which is just to take your original data, fit your PCA model to it, and then look at the residual. Okay, so the idea is that if it's just speckles, then you should end up with more or less emptiness, Gaussian noise if you really believe your model. But if you have a companion in that little patch, then there should be the PCA model will not fit the companion well. So that's a key assumption. And you'll be left with a residual signal that you could then correlate with some known fixed companion model, which you've got offline from somewhere else. So that's a very, very high-level summary. Now, this one thing I'll come back to in just a moment, the basic flaw with these kinds of algorithms of sort of fitting a model and then just looking at the residual for the thing you care about is that if the model's got too much capacity, so if you increase the number of basis components here, at some point the PCA basis would start to model the companion signal too. So you wouldn't see the companion at all. And so therefore, with these things, there's a very important tuning knob, which is how many components should you have in your generative model, or what should be the capacity of your generative model. Now, in the detection, so that's a generative model. It's not, strictly speaking, if you're being rigorous, a true generative model of the data, but it is nevertheless a sort of a generative approach to doing things. So notice that we didn't need any labels exactly. So this PCA basis you're seeing here, this was estimated from the green region. Okay, so for each of these different angles here, you get a different patch, and then we would take that and then you throw that into the PCA algorithm. But we don't need any sort of explicit labels here to be able to train the model. Now, in the discriminative version, we do need to get labels. This is so that what we have to do is you're going to, for each radius and angle offset from the center, you're going to have to basically create your own little fake data set. Okay, so you can take the negative data directly. You can assume that, okay, there's only a single planet, perhaps at any given radius from the host star. And then what you're going to do, though, is to train your discriminative model, you will need positive examples. This relies upon you generating now a whole set of positives examples by inserting fake companions with realistic brightness and some realistic spectra. So in practice, they had a sort of distribution over spectra, which they then sampled from. So they got a sort of a particular spectra and then used that to create a particular example, and then did that again and again. So there it is now. They've got a sort of a training set of explicit negatives and positives from which they can train their support vector machine. And on the training set, which is this collection of data here, and then they, sorry.
I'm just asking, do the positive examples also need, do you also need to create some artificial speckles so that they have different speckles?
So what you're assuming is that the speckles you're getting will be, you can use the background speckles basically as your speckle distribution. So yeah, I mean, it's, ideally you would also be able to generate new examples of speckles too. In this particular thing, they didn't actually do that, yeah. So they're sort of they're going to add, they simply, add in a companion signal to a patch drawn from what they hope is the background speckles, and just add the two and use that as a positive example. And then what they're going to do is to take their SVM and throw that at this data set. Sorry, once they've trained the SVM on the training set, they will then take it to the held out region, to this thing here, and they will evaluate, they will get directly from the SVM some score as to whether they think there's a companion there or not. Okay, so just a contrast. Basically, in this case here, the data is just simply the speckles. When you're training the model, you're just going to be using speckle data from the held out, from the training part of the annulus. In the DS4, you'll have to generate the data too, artificially. This is using PCA to model that data. This is using SVM. And then the detection is done here by just correlating the residual with some template. Here it's just coming directly from the model. So just to give you a little example, so this is these are the discriminative models. This is the type of SVM. So this is the linear separation. That's the linear decision surface. This is using a slightly more complicated decision surface, which isn't linear. This is the generative model down here. So what we're looking at here is sort of heat maps after you've run the speckle suppression algorithm. This is different difficulty levels. So this is showing the relative brightness compared to the speckle flux at any given location. So the magenta box shows the ground truth location of this fake companion that we've inserted. And so what you would hope, of course, is that, and this is a good example here, sorry, the projector may not be showing it very well, but you would hope to see just a single bright blob inside the magenta box. Okay, and when you get down to lower signal strengths, you can see there are many other bright regions in the map too. So this is the jet color scheme. So red is sort of high and blue is low. So in this case here, you can see at least at 4%, there's a clear difference when you use this more sophisticated SVM approach compared to the generative model or indeed the linear thing. So you see a single strong peak and nothing else. When you get down to these other ones here, it's still probably slightly better than the generative model, but the differences are less clear between the two. So typically, if you've got enough data available, discriminative methods usually do win out. It's difficult often to train up generative models with enough capacity. So I'll talk about that just when I close. Okay, so just to talk about one of the nice things about generative models is that you are able to sort of understand what they're doing much better. So for example, those big neural nets that were classifying images, they are a complete black box. No human has any real idea what is going on inside them. There's 60 million parameters in there. Somehow an image comes in and out pops an accurate prediction as to what's in it. And that's very frustrating from a scientific perspective. So what I'm going to talk about now is a generative model. It gives you an example of the kinds of things you can do with generative modeling, which actually are very useful in science, where you do actually want to understand what's going on. So in this version, in the previous version, we had essentially a fixed companion template, which we assume had a white spectra, or a spectra that matched the companion star, or something like that. Now, what we're going to do in this approach is to this is more than beyond a simple PCA model, is to treat the spectra as an unknown variable that we're going to estimate along with the speckle basis and things like that. So we're going to essentially explain our observed data by this PCA model of the speckles plus some fixed spatial model of the companion, with some latent spectra that we're going to infer as part of the model fitting procedure. And we're going to sort of assume that we have Gaussian noise between our sort of reconstructed version of the signal and the observed data. So this is just a little sort of key figure that summarizes the algorithm. I don't really have time to go into the details, but this is the speckle part of the model. This is the planet or companion part of the model. This is the reconstruction from the model, and that's the observed data. Okay? So what's going to happen is you're going to, the things in green you will adjust on a sort of per exposure basis. So the idea is that you will have, you're looking at a single location now in the field. So you're trying to now separate this, this signal out into the speckles and the companion along with its spectra. So basically, here's your speckle basis that you've estimated from your training part of the annulus. These are the coefficients, so these are the weightings on each of these bases. And when you sort of multiply 1.2 by that guy plus minus 0.11 times that guy, you end up with this. So this is your generative version of the speckles. So this is your estimated speckle component. And then on the other side, you have this fixed planet model. And then you're going to apply a spectra. So in this case here, the spectra is just, it's normally 32 wavelength bands. In this case, I think it has 23 for some reason. So this will, each of the coefficients here will adjust the horizontal weighting, as it were, of each of these. So the wavelength is on this axis. So when you apply this to this, you get some sort of weighted version of this planet, weighting by different wavelengths. And then you add those two together to get this signal. Okay, so this is what I was referring to with the whole top-down generative procedure, because you're sort of, given these variables, you can generate some version of your input data. Now, of course, given the input data, what you need to do is to infer the stuff in green. You need to go backwards up the model and work out what the coefficients are on this thing and what the weights are on this thing. Now, fortunately, this thing looks a bit scary, but it turns out this is still this is actually a constrained optimization problem that you can handle. So it's constrained because your your companion flux has to be positive overall. But you can solve this with standard gradient descent with some constraints that enforce this thing to be positive everywhere, or non-negative everywhere, because it could be 0. So that you can run this model on the data from P1640. And so we sort of tested it out by putting in some fake companions. So we picked fake companions that had realistic spectral profiles, and then the signal strength was designed to be somewhat similar to the real companions around HR8799. And so what you can see here is the black is the ground truth spectra, and then I'm showing here in the different colored fits the results from the generative model I just showed. And you can see it does a reasonable job of fitting the data, even though these are actually quite weak companions in the P1640 data. And I guess the key point from a sort of machine learning point of view is the thing you really cared about was an explicit variable in the model. Okay? So if you had a discriminative approach for estimating this thing, it would be much more complicated. You'd somehow have to take this thing and directly build some very complicated function that would output this. Okay? And you can see that's going to be quite a hard thing to do. You would have to create a whole bunch of fake data with different spectra and so on and so forth. It'd be an interesting thing to try. I'm guessing, though, that in this particular case, where you have a very good understanding of the formation model of the data, this sort of approach here is likely to probably work better. So that's actually, I think, sorry, I'll come back to that point at the end. I don't want to get ahead of myself. OK, so for fake data, this worked quite well. And then there was a paper that Rebecca Oppenheimer and others, along with myself, had a few years ago where we applied that algorithm to the companions around HR8799 and showing. We tried to get we tried to do some kind of uncertainty map on these measurements. As you can see, for the ones close in, the E companion, the error bars are pretty large, but for further out, they're not too bad. Now, this idea of sort of doing good generative modeling of the data, there's some colleagues of mine at NYU, so David Hogg and Dan Former-Mackey, who's now at UW, they use this another different type of generative model for Kepler data. So this is actually the Kepler 2.0. So the reaction wheel's broken on the spacecraft. They can't hold it completely still. So the raw data is kind of a mess. So what they did was to come up with a little generative model where they had a model for the planet. So they understand the physics of how the light curve should dip. Sorry, let me just say, this is transit-based exoplanet. So they're looking for sort of this dip when the planet transits the star. They've got some model of stellar variability. They also have some model based on the dynamics of the spacecraft to explain that, and then they have some detector noise, okay? And then the idea is that those, each of those, all those signals will be added to reconstruct the signal. And so the inference procedure is, given a nasty, ugly signal like that, back out each of these 4 different sources that contributed to it. And indeed, they've actually been quite successful. So this thing really does work. They found 36 different planet candidates, and 18 of those have been confirmed. So this is very much the same sort of, from a machine learning point of view, philosophy as that S4 Spectra model I was just showing. Again, it requires you to have a good understanding of the formation process of your signal, and that for each of these different causes, that each of these different components that contributed to that signal, you have to have a good representation for it. So you need to know, what's a good model of stellar variability and things like that. And just as this is, I may not have time quite to get through this slide, but this is just showing what happens if you try to take, this is a light curve from the Kepler data. They put in a synthetic planet transit. If you try to do a silly PCA fit, this is very similar in spirit to the S4 Detect model I showed earlier. What happens is, if you have a few principal components, you will leave systematics in the signal, but you will still see your planet transit. But if you increase the number of PCA components to remove your systematic stuff here, they go away, but you start eroding the actual signal you care about. Okay, so this is an example of just a naive fit, and then looking at the residual doesn't really work very well. Whereas in their sort of joint modeling of both the companion and all the other stuff going on, they can remove the systematics and correctly get the strength back of the planet transit. Okay, and so that same argument applies to S4 Spectra in the sense that you're simultaneously modeling the speckles and you're also modeling the companion signal too. And that's from a sort of probabilistic modeling point of view, that's the right thing to do. You should fit these things simultaneously to your input data. Okay, so just to wrap up, I just wanted to spend a few minutes sort of comparing and contrasting the different sort of schools of model you can have. Okay, so in discriminative methods, you must have labels, right? You must have some target that takes your inputs, to aim for given your input signal. So you're given an input image or whatever, and you have some big high-capacity model, and it's going to spit out some kind of label or some quantity you need to, some quantity you're trying to regress to, and you must know for each training example what that target should be for the model. So this means you can only do supervised learning with these discriminative models, and what you're doing really is you're only modeling the decision surface between the classes. So for example, going back to the natural image classification, you're not trying to, the big deep neural net is not modeling what all dogs look like. It's only modeling how dogs separate from cats, and then how cats separate from hamsters and things like that. Okay? Whereas if you had a big generative model, you would actually have to model what every single type of dog could look like. But the beauty of doing that is that all your modeling power is going to that decision surface, and that they can be very powerful, as we saw with the deep neural nets. Now, the generative models, we don't necessarily need labels for them. If you have them available, you can use them. You can train unsupervised. So for example, that PCA fit of the data I was referring to, that's actually an unsupervised learning. All you're doing is you're just modeling the data density, as it were, of those speckle patches. You are modeling the whole density, which I think if you want to explain your data, that's philosophically what you should be doing. Right? Whereas, just to be clear, in the discriminative modeling, you're not really explaining all the data you observe. You're only really looking at the sort of ones that are going to affect your decision surface, which is maybe a very small subset of your data. And the plus point is that often you do get some interpretable result out of your generative model. But the difficulty is you must be able to specify the model structure. So for example, just winding back to this Kepler algorithm, in this case, they had to have a good model of how they got the nasty light curve in the first place, right? Now, in astronomy, in general, you do actually have that, which is you do not have in other domains. Like, for example, in modeling natural images, if you wanted to model an image, natural scene, you would have to model all the lighting, your object occlusion, the fact that objects are 3D things that can rotate, and so on and so forth. And that's why discriminative models have completely won out for sort of tasks in computer vision. I think astronomy is very interesting because you basically have very good physics that informs the model structure, and therefore you can use that effectively. Now, I just want to the last point I want to make is that just hearing the first two talks this morning, which I thought were absolutely fascinating, one thought that occurred to me is that really, we think of sort of the instrument and the machine learning algorithm as two sort of disjoint things. We'll get some data from the instrument, and then we'll run some sort of machine learning magic on it, and out will pop the planets. Just to say, I think one thing we might want to talk about at this workshop is the idea of kind of using machine learning to help design the instrument itself. That is that if you have some model of what you're looking for, so if you have some statistical model of what the speckles would look like, you can sort of, perhaps adjust the characteristics of those speckles so that you'll be able to pull out the planet more easily. And this is a super toy. This is a previous paper I worked on, which sort of gets at that concept. This is, high school science project level optics. So this is a piece of cardboard we cut out with a very precise pattern and inserted into the aperture plane of a standard digital SLR lens. And the objective here was to try and use a standard camera to be able to get depth from defocus. So if you're focused at a certain distance away from the camera, objects closer or further from you will be defocused, and the amount of defocus will tell you the depth. And the question is, from a single image, could you get depth back? And the answer is you can't do it normally with a normal aperture shape when you have like a hexagonal or whatever aperture shape your lens has. And what we used was actually a generative model of natural images to design this hardware. Okay, so we spent some time, we had a model of what natural image patches would look like and played with shapes of aperture that would sort of maximize the difference in statistics between different depths of blur, different amounts of blur. Okay, so basically what I'm trying to get at is by understanding the signal we were working with, we're able to sort of use machine learning to kind of figure out a better piece of hardware that would let us then actually get some kind of, it's not a very accurate depth map, but get some kind of crude depth map back out for free in addition to your just taking a single picture. Okay, and I wonder whether you might be able to do something somewhat similar to that with the coronagraph design itself. If there were some parts within it you could have either under control of the algorithm itself when it's running, or perhaps you could use it to help design it and then lock that design. Okay, I'll stop there.